So, good morning, everyone. Welcome to the 11th week. That will be like the second last week of the course. And of course, the course is the joy of computing in Python. So, once again, if you have any questions regarding last week's lectures or like any of the previous classes I've taken, feel free to ask and I'll try my best to explain it to you. But otherwise, what I'm planning to explain today is a little bit of continuation of last week's class first, and then we'll move into a very important topic which I'm confused for some reason is not taken during the course, and that is the concept of classes. So, once again, if you are feeling that what I'm doing is too easy or something like that, feel free to the questions above me. Okay, so in the last week, I had shown how to like make a picture of the maze. So essentially, given a maze like this, where W represents the walls, E represents the end, S represents the start, and O just represents the path that can be taken. How we can make this into a what are they called into an image. So if we run this, because of the code I've written, I can write a set. Yeah, so you can see like this maze corresponds to this picture of the maze where this is the start, this is the end, and you're supposed to go take this path. So the first thing we had done last class was not involving functions. We wanted to logically figure out how to convert this into this. So the first step, we obviously need to know the number of rows and columns. I hope this things make sense. The initial maze is given as a string, so the number of rows in the image will be the number of uh, lines in the text. So the row is the length of the number of lines, and the number of columns is how many there are in a single row. And thus we can get the number of rows and columns. After we have number of rows and columns, we can imagine this image as patching together a lot of small images. So we'll have a Control C. So from the last week's lectures, we know how to make images directly from the Pillow library, and you can ignore this. So let's say the size of each of these squares is 50 into 50. So here I'll be making all the each patch is required to stitch. So if I print one of these, we'll get walk will just be a white thing, wall will be black, and path will be a shade of gray. So with this, we can kind of logically figure out how to make this image like step by step. So we start from the top left, and depending on which letter we are, we start here. And if you see a W, that means it has to be a wall. If you see a E, it means it has to be the different shade, and so on. So I'll just add that here because this is the old code. If letter is equal to S, else. Okay. So that's how we get this. If you the code essentially goes as if we go through, we have the text, the maze is right now a text of from everything, and then we go line by line. So in the first line, we'll have the value of I is 0. If you remember, enumerate is a function that just counts a number of things. So maze dot split lines will give me the first line and the second and the third and so on. But if I put enumerate of maze dot split line, I'll get 1 comma the first line, 2 comma the second line, and so on. Likewise, I'm using an enumerate for this thing also. We need a strip at the end because the last line of every line is always the next line character, and that's necessary. So now so that is how we can make this image. But working with letters is like kind of inconvenient. So the first thing I would have done to make this nicer is to just convert everything to numbers. And we can, when you're converting to numbers, we can start using the NumPy library for quick access to things and so on. So I just got these numbers for convenience. You can change these numbers to whatever you want, provided you change them correctly. Now, instead of like drawing the image like this, I would want a function called draw, and which I've written later, but we'll explain. I'll explain about this function in a while. Before I talk about this draw function, I need to make the maze array. That is, instead of a string input, I want a number input. Writing this in a string is reasonable because it's humans are much nicer writing letters than numbers. So I want my input to be like this, but I want the computer to look at the maze in terms of numbers. Yes, Shashi, do you have a question? He left. Okay. So I try to generalize what I had done earlier. First, we need to find the number of rows and columns. So I do the same thing as before. I get the rows and columns using the same things. But this time, instead of having a string, I want to go with work with the array, with the NumPy array, right? So I define a NumPy array which is filled with zeros. This is so that I know the dimensions of the thing. The size of the maze does not change as I run the program, right? So it's reasonable for me to fix the size of the array within this line. What NumPy, why this is nice is NumPy will give you errors when you try to access wrong elements of the array and all. For example, if I temp is equal to np dot array, np dot heroes 2 comma 2. So this is going to make a small array of just 2 comma 2, just 4 elements. But say I access the third element, we will get a proper error, and I feel like this is the way we can like check the correctness of our code. Like if you do this on a string, you'll probably still get a nice number, which might not be what you want. So first I'll do this, and and secondly, here I access the element by giving two numbers. I give temp of 1 comma 1, which will give me the first 1 comma 1 element. Okay. if I still had the string, if I used this, yes, Pallavi, there are recordings of the previous week's lectures. I will show it to you in the just after I explain this small portion. So where was I? Yeah. Oh yeah, if you have a string, then to access this element, you have to add the number of things here, and then you have to do a little bit of calculation to arrive at this element. If you use a NumPy array, you can get this element by knowing the row and column index, and that's it. Although therefore, it's just significantly more convenient to use NumPy arrays to go to access two-dimensional data. If you think about it, it is a two-dimensional data. Before that, I will just continue about, so if you open your Swayam portal, you can go to problem solving session, and there'll be a link here. If you open this link, you will be able to get all the YouTube links. So if you come to my YouTube channel, like if I open this, there should be a playlist. Yeah, there'll be a playlist with all my classes. So I'm sure the other TAs have also done similar things, but this is how you'll access all the classes, all the recorded lectures. Pallavi, were you the one who asked me the question about Clahe the last week? I guess not. Okay, so where was I? Yash. It's too far down. Okay. So this part is almost exactly like what I have done here, except instead of pasting an image, I am putting the correct value inside the maze array. And you can see that the code here is kind of intuitive. So after you run this code, you will have a maze array. So if I run this, we have all the zeros and ones to properly do these things. And now our draw function should just take this maze array and we can do things nicely. And the code here is almost exactly the same as the code above, except, yeah. Now we'll come to the crux of the problem, to actually solve the maze. So okay, give me a second. I'll take the more complicated maze. Okay, this is like a super complicated maze. I'll just we can ignore this for a while. Okay. So one way we can solve a maze is kind of a trial and error method. We take a route and you just keep taking that route until you stop at a place. So in this case, I'll just keep going like this. Okay, wait, give me a second. O and E. Okay. Okay, so I'll just keep going forward until I reach the end. And if I reach an end, I should go back because I know this route is wrong now. Then I go all the way back until I reach a part which is like a junction. Essentially, the main problem will be all these places which are junctions, because only at junctions where do we have a decision, should we go left, right, or any other direction. So once we reach a junction, we can take the path again. We reach another junction, we go here, we are stuck again, so we have to go back. Once we go back, we go to the other part of the junction, and fortunately this time we reach. So there is like two parts of this code. One part is to just keep going forward until you reach the end, and the second part is to backtrack until you reach a junction. So those are the two important things we need to do when you're trying to solve a maze. So before that, I feel like one fun thing we need is we need functions to define, what's that thing called? We need functions to define directions. Like instead of calculating these every time, I feel it's more intuitive if you make functions to do it for us. Because one inconvenient thing is when you're going up, you need to make sure the value of x is less than 1. So if I'm in this row, I shouldn't be allowed to go up. Likewise, if I'm in this column, I should not be allowed to go left. So I define these functions in a way that if I just return the correct position, provided I am allowed to go there. So I guess this function, these four functions will make sense. Left takes you to the left, right takes you to the right, and so on. Okay, so another useful function. Okay, so another useful function is, given a point, how do I control C? Okay. So imagine I am here. If I am here, I'll have three places I can go. I can either go here, or here, or here. And that's like three legal places. But if I am instead here, that's 10 is 7. If I'm here, there's only two places I can go. I can either go here or I can go here. So it's a useful thing that I should know what places I can go given a point on the grid, right? So I define a function called get legal directions. That is what places I'm allowed to go. I will talk about the backtrack part in a while. That's not necessary right now. So given a point, I must find which directions I can go. And I first find the x and y positions from the point. And this is what I'm going to return. So naturally I call it return. I call it ret. We can ignore this right now and let's just say check is equal to walkway. So in addition, like if you're here, 7, if you're here, you're allowed to go here and you're allowed to go here. So technically one of the places you can go is not just the walkways, you can also go towards the end, obviously. I hope that part was trivial, obvious. Okay, anyways. So check is just to make sure I am those are these places. I'm calling it check because I'm checking for these. another reason is eventually when I'm going to implement backtrack, I will show why modify check accordingly. So one very logical way we can do it is I first check. Okay, so before I do anything, I must explain a small but useful function, or rather operator. Here, I'm not saying if cell is equal to left of x comma y. I'm saying cell colon equal to. The colon equal to is called the walrus operator because it looks like a walrus. Okay, I'm not joking. It's actually called that. So the thing, what the walrus operator does is sometimes you have functions that return nothing or it returns something, right? And if it's returning nothing, I'll have to check if it's returning something first. Like if I say up of 0 comma 0, it doesn't return anything. But if I return up of 1 comma 0, it returns that, because if I'm 7, if I'm here, I can go up, but if I'm here, I can't go up. So this function up sometimes returns something and other time it doesn't. So one thing which can be convenient is I have to store the value of this if it returns something. So we know that if it returns something, we can just do if this, and then cell is equal to up of 1 comma 0, and that will give me the value. Print cell. So this will print this, and if this is 0 comma 0, it won't print because it's not returning anything, and because it's not returning something, that's inherently false. But that's a little bit of, you have to write an extra line. So Python made it easier for you to consider cases like this with the walrus operator. So if you want to just skip one line of code, you can use the walrus operator like this. And honestly, this is the main reason they introduced the walrus operator. So what the walrus operator does is, if this is true, I'm assigning cell to that. If it is false, I'm not assigning a cell to anything. So that's what I've done here. If cell is true, if left gives us if this is a legal operation, I assign cell to that. Then I go to the maze array and check that cell. That is, what is happening is, so say I'm right now here. Say I'm right now here. Up, the first one is left. So when I check left, it will first check left and it will look at this cell. When it looks at this cell, this is a walkway. That means it's a legal place I can go. So maze array cell, it checks if I can go there. It turns out I actually can go there. So I add it to the list I want to return. Then it checks the right. So I'm here. It goes to the right. I get this cell. I get the location of this cell. Once I get the location of this cell, I check in the maze if that cell is a legal place to go. And yeah, it's a legal place to go. So because it's a legal place to go, I append it to the return value again. Then I check up, but up seems to be in the wrong place. So I first find up, and then I check the place, and because it's not a valid place I can go, I don't append it, and so on. So for example, if 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 6, 2. Oh God. Oh yeah. So like, because this is a list, I need to put. Okay. So just ignore the last part. So it gives me 1, 3. 6, 2. Where is 6, 2? Uh, oh, 6, 6, 2 is here. Okay, then that's nicer actually. Okay. So 6, 2 is here. So in 6, 2, the only two places you can go is right and down. And so the function returns 1 and 3. 3 is down, 1 is right. So that means you're correct. The function works exactly as we want it to. I hope what I just did made sense. Okay, so a couple of people came new. I'll just quickly explain what's going on. So last week we talked a little bit about how to solve a maze. So I've written the code out and explaining it line by line. After that, I'm planning to explain a very important concept in Python called classes. And I feel like it's be a very useful for all of us if you go through the basics of classes at least. And once again, if you have any questions regarding last week's lectures or any of the previous weeks, feel free to ask and I'll try my best to explain. And if you feel what I'm doing is boring, you can do like more interesting questions above me, which is like much harder in my opinion. Yeah. So that is how legal directions work. So now we just need to we have the legal directions, and I think we have all the framework needed to solve the thing. So there are, so because I just keep running the code again and again, I'm putting a reset here because I want to reset the code every time I reset the maze before I solve it. And when you start, you're obviously at the start position. And when you're starting, you're obviously not backtracking. So now let's think about how the backtracking thing works. So when you are going forward, okay, so logically let's okay, I'll just add an extra box here. Okay, so say we can access this box also. Is there a nicer way to? Oh yeah, okay, I can do it like this. So W. And yeah, so I just shifted this wall to here because I wanted a quick way to show the backtracking thing. Copy you. Okay, so before we go forward, we need that essentially one thing to do. We need to, because we need to backtrack our way, think of it like as you're going to different places, you're leaving breadcrumbs behind. So when you're leaving breadcrumbs behind, you can follow the breadcrumbs back, and that way you won't get lost. So you'll go forward, leave something behind, go forward, leave something behind, and you keep doing that. In that case, you won't get lost, because as you come back, you can just pick up the things you left behind every time. So at start, I'm starting at the start position, and then I go to the, I look at the all legal positions. I see I can go here. So I'll go there and put a breadcrumb here, and then I'll know that I can go because of the get legal directions. I know I can go to this place or this place. So I'll choose a random direction among that, and I'll go to the let's say I go to the right instead. Yeah. So I'll go to the right. I'll leave a breadcrumb there. Go to the right, leave a breadcrumb there. Go to the right, leave a breadcrumb there. I again have a choice. So let's say this time I wrongly chose down. So I'll go down, leave a breadcrumb there, and so on. And as I keep leaving breadcrumbs, I finally reach a place where I'm stuck. Since I'm stuck here, that means I made a mistake somewhere. So I have to now go all the way back and pick up all these breadcrumbs, and until I reach a junction. So this is the backtrack part. So if you go back to the get legal directions, where did it go? Yeah, in the get legal directions, the legal directions depend if you're backtracking or not, because if I'm here, then even though there are two ways I can go towards the right or towards the left. I don't want to go to the left, because here I've already placed a breadcrumb. I should only go towards the left if I'm going to backtrack. So the direction you go depends on whether you're backtracking or not. So Control C. So if I'm not backtracking, I'll go to the normal way, either the walkway or the end. If I am backtracking, the only thing I need to check is the breadcrumbs I've left behind. So that's what we'll do. So we need to make sure we are, when you're starting the thing, we are not going to backtrack, we need to go forward. So now we enter a forever loop. Essentially, we just keep going some places until we reach the end, or we are genuinely stuck. If you are genuinely stuck, only happens in one case, and we'll talk about it when we reach there. So at the beginning of when we are entering the loop, we are obviously at the present position. Actually, we can make this nicer if I, yeah. Okay, every time I start the loop, I will draw. And I feel like this way we can better see what's going on. So let's start debugging. So now we have just okay. Why didn't it draw? Oh yeah, it. put in the code above. Give me a second. Okay, yeah, okay. So we start like this. Control. Oh, give me a second. Oh, okay. Okay, so it first checks. So right now we are here, and obviously that's not the end. So this part will just continue for on. It checks if you are backtracking. We are not backtracking, so it will just continue on. Now it gets all the legal directions. It will find that the only legal direction is upward. Okay. Now, if there are no legal directions, that means we know we are stuck. So we look at that. We'll look at this case when we have Fokker circulator. If the number of legal directions is more than one, that means we are at a junction. And if while there are other ways to solve this, I feel this is a nicer way, because if I'm keeping track of the junctions, then it's easier for me to, if I'm keeping track of the junctions, then it's easier for me to like know when to stop backtracking. So I'll just, right now I'm at start, which is not a junction. So it won't do anything here also. So at this point, I'm realized, okay, I can go to some place. So I'll put a breadcrumb where I am. So at my present location, I'll put a breadcrumb. I'm putting a backtrack, and I go to my next position. The syntax here might look confusing, but that's because I've done a small hack to make it in one line. Now the loop continues. When the loop continues, why did it just stop? I forgot. Okay, so I forgot I changed this. Now, here I will tell you what that small hack is. We first put 0, 1, 2, and 3 to denote the directions. And yeah, that works. Like, given 1, 2, 0, 1, 2, and 3, I'll know where to go. But instead of 0, 1, 2, and 3, why not just give the function itself? So instead of saying if 0, do up, if 1, do right, and so on, I'll just go left, right, up, or down, depending. I'll just return that itself. So I've spoken to you earlier about functions that take functions and do things. Here I'm having a function that is returning a function. So Python is like very fun in the sense that you can have functions that return functions as well. So this is one such example. So if I run this, the legal position at 6,2 is the right direction and the down direction. You can see how this is like very neat. It's kind of a fun thing to do. So yeah, so I had changed that code. I had forgotten to fix it again. So Now we'll properly debug this. Oh, it's crashed. Okay, so uh, give me a second. I have to. What's this? Start again. Okay, so now it should work fine. Okay. Okay. I'm sorry for that. Uh, snafu. Let's continue. Okay. So we'll just. So we have first here, and we'll just keep. Let's keep going forward. Okay. So as I said earlier, because because get legal direction. Okay. Because get legal direction gives me functions, I can now call those functions using this using the normal syntax. So get legal direction gives me an array of functions. So legal direction of 0 is the first element of this array, and I'm calling present position from the from this function, which will give me the new position. So if I continue, it'll take me here. There's no difference here because I've only put the backtrack here so far. So I'll just keep going. So now I've reached here and I've placed breadcrumbs here, and I've gone to either this place or this place. We'll get to know after I print the value. So let's just keep going. So it turns out we made a wrong turn, and now we are at a dead end. Because we are at a dead end, we'll properly see how the backtracking things now work. first it checks that we are not in the present correct place, which we aren't. And now it checks if we have to backtrack. Control Alt, no, Control Shift. Okay. Because we have reached a dead end, we have to backtrack. So now because we have to backtrack, we also have to check if we are at a junction or not. We are right now here, which is not a junction. So we'll go a step back. Because we are not at a junction, we can just do the normal things. That is, first get a legal direction. The legal direction here is to go left, is to go right. So we can actually check that. So if you go to legal directions, you can see the legal. If you look, legal direction is the function which is right. So here it knows it's going to the right because that's the way we are backtracking. Now, what I have also done is when you are backtracking, we close off that place because we don't want to go back there because we know that's the end. So I'll just wall it off. So I wall this place off and then I go to the next place. Now I've gone back here. Since I've gone back here, I've not just gone back there, I have also walled this part off. Because I've walled it off, there are no more breadcrumbs there. So now I'm here. Because I'm here, it will, and this part is a junction. So because it's a junction, I no longer have to backtrack. I can just stay here. And I can now just continue going forward. Now, because this part is walled off, I can just ignore that place and go to the next place. So right now I'll be here and we can see that in the next part. So because I wall this part off, I can only go here. So I'll just keep going forward now. Actually, I should make a. No, never mind. Okay. So, well, so that is how the thing works, and I hope the steps kind of made sense. After that, we have seen what it happens at junction. We saw what happens when it's backtracking, and we saw how it happens when it's normally going forward. So this essentially just keeps doing that until it reaches the end. So let's see, just run this and see. I have to comment it. Please don't do this. Okay. Okay. The thing is, this runs very quickly, but printing the image takes time. So now that since I've finished it, if you just draw now, it has identified the correct path. While it looks like magic, essentially all it did is repeat the steps, step one by one. In fact, one of the fun assignments you can do is to like make a GIF. You can using the pillow library. Where did pillow? Yeah, so in the Pillow library, you can also work with GIFs. So if you read the documentation a little, you can understand how essentially, where did it go? You can just take a GIF and just slowly put images at the end of it, and that will work. There might be something here extra about GIFs, but yeah. So one fun assignment is like to show how this thing generates goes and makes mistakes and goes towards the end of the file. So that kind of concludes about the solving the maze. We can even go look at the other maze. Where did it go? Where did it go? To So this is a smaller maze, the maze I showed the other day. And if you do the same algorithm, it will solve the maze correctly. Okay, so now let's talk. Okay, so that kind of concludes the maze part. I hope that part was a little interesting for you. So one thing I tried to like not scare you was the concept that this is a known algorithm. What we have solved right now is something called depth first search. Depth first search is essentially you try to go as deep as possible, and if you made a mistake, you backtrack and keep going to the next places. So that is what depth first search means. Depth first search. These are awful images to explain depth first search. Okay, this kind of shows you. Essentially, you keep going all the way towards the end, and if you reach the end, you backtrack. That's what depth first search is. And that is kind of how we solve this. Backtracking essentially means doing depth first search. The other idea for solving mazes is called breadth first search, because instead of going depthwise, you kind of go sideways. I'll explain using the so in depth breadth. Okay, so I'll just compare it like okay. So depth first search was we go all the way towards the end and come back. I go here and then I come back, and then I go here and then I come back, and then I go here, and so on. What breadth first search does is think of pouring water into the maze. So I'm pouring water at the start. The first place to get water is here, and then this place and this place will get water. But now this place is stuck, so it knows that's a dead end. After, if I continue to keep pouring water, it will go here, and then it will go here, and then it goes here and here, and then it goes here and here, and so on. So as you can see, this is like water spreading towards the maze, and it just keeps doing that until it reaches the end. Once it reaches here, it will go split in both direction. Go here, go here, go here, go here, go here, go here, and then here, and splits again. So here you're like branching out in all places at the same time. This is called breadth first search, and solving this is also another fun exercise for you. And I will not be explaining how to implement breadth first search. Like, it's not difficult, but it takes practice to properly get it right. Okay, and so though that's like the main two graph traversal algorithms, there's slightly more things. There's something called the A-star algorithm, which is like depth first search, except when you're in my depth first search, you randomly choose a direction at every junction. In A-star, you choose a direction which takes you closer towards the end goal. So if I Control B, if I have a depth first an A-star algorithm, I'll go here and I won't go towards the left here. I'll go directly to the right because that's closer towards the end. Here I'll go up because that's closer to the end. Here I'll go right again, and apparently if you code A-star, you'll get the optimum solution immediately, but that's not always the case. But that's how the A-star algorithm is. So in fact, you guys can try coding the A-star instead of what I just coded. So I'm just giving you a lot of exercises you guys can do to like improve your coding skills. So just once again, you only get better at coding with practice, and just listening to people code, it really doesn't help that much. It's called the tutorial hell. Like, once you're in the tutorial hell, it's very difficult to get out. Anyways, so now let's talk about classes. We can save this. Close this. And we'll talk about classes. So the concept of a class, so you might have not noticed, but everything you've been working with so far were actually classes. For example, whenever I have hello there, this is actually a class, because if I type how do I show? So I can't show this quick. Okay, I'll just quickly import numpy. Import numpy as np. A is equal to np dot zeros. So the thing you see, how am I supposed to point it? Okay, the thing you see here, that is the class type. That's the data type of the thing. So what exactly is a class? A class is just a bundled data of, it's just a bundling of data. So control this. Okay, let's go to class. So for example, a student can be just a bundling of a name and an age. Yeah, there are more things that make up a student, but let's think of a very simplified version of a student. This might be too simple, but let's just think carry on. So any student needs to have a name and an age, obviously. So that's what this does. When I say class student, I'm saying every student has a name and an age. I just ignore this for a while. I'll come across this later. So the thing is, so when I make a new student, I am a student, so when I'm making a student, I'm saying my name is Naveen and my age is 25. You can see that's written here. Okay. So when I run this, it will. Okay. So another more important thing is, I said it's a bundling of data. So right now, me contains Naveen and 25. So and 20 Naveen is stored under the name and 25 is stored under the age. So if I put dot, Python knows what I'm kind of expecting. I can either ask for the age or I can ask for the name. If I put age, it will give me 25. If I put name, it will give me Naveen. So that is the idea. So essentially, student is like a blueprint. A student needs to have these things. One. I am student. Make it. So I am a student, and my characteristics are Naveen and 25. I can make other students also. I'll call him my friend is also a student, and his name is without loss of generality. We'll call him without loss of generality, and his age is in. Okay, I have to give a number. His age is 42. So just like I have a name and I have an age, even friend will have a name and an age. My so it's kind of intuitive, right? Me is like a mash of a name and an age, and I can take the name using the dot. And that's very similar to what we did in NumPy, right? So if we wanted the shape, we'll do a dot shape, and it gives us 1, 2. This is very similar. So many of the things you have seen so far are classes. So just a small, I'll explain a little bit more about the notations. So let's take you and move you up. I'll make it smaller. Move you up. Okay. So this will be this is the class. The class is a blueprint. Okay. The class is a blueprint of what I expect every student in the class to have. I am a student, right? So this is an instance of the class. An instance of the class means it's not just the class, it's a class with actual values inside. And I'll just clean this up a little. Okay. The proper terminology for this is an object of the class. This is an object of the class, and this is the core principle of something called object-oriented programming. That is, every part of your code is an object. And Python like properly simplifies this. So does many other languages like JavaScript and especially Java. Hmm? You may ask, what's the advantage of writing things like this? Oh, what is it really used for? The thing is, in addition to objects having data, the primary thing is objects can have data and functions. Remember, when you have a when you have this numpy array, we can have dot many a lot of functions. All of these are different functions associated with the numpy array. Obviously, argmin will give 0. I'll give 1. Three comma 3. Just print a. So right now I've made a random numpy array, and argmax will identify the row with the largest element, argmax, and the largest element is this, right? So, and if I do anyway, my point is, in addition to data in terms of variables like name and age, I'm having functions also, which functions which allow me to get data from get information I need from the thing. So for the notation for that is very simple. So it's just like how you define a function. So def introduce. No. Let's make a function that shouts. And all I have to do is I have to shout my name, right? But I have to shout my name. This object. So when I do, I'll just put a pass here. So I should be able to do me dot shout name, right? Because this shout name requires the object itself, I must give this the thing called self, because it needs to have its own data. Before you ask, yes, you can be a little there are function calls which does not need self, but that's a much higher topic. So once I give self, I can take any of my values. So I can take self.name, I can take self.age. So the thing is, here I'll do me.age, me.name outside the class, but inside the class I have to do self.age. So let's print self.name.upper. So just as you'd expect, if I do me.shout name, it shouts my name. Similarly, I can make other functions like def. What's the name of the function I wrote here? Okay, I have a function called say age. Similarly, as I said before, I need to put self so that it knows it needs its own data, and I'll do print my age is f. My age is self.age. I'll make this I am and not all not that's not all. I can have functions that call other functions. So I can have def introduce, which takes self and it calls other functions. Self dot shout name, self dot say age. So if I do self dot introduce now, it will just do what you expect it to do. It first goes to inside the class, looks at it needs to do shout name first, and then it does say age, which is what the output, the expected output is. So the idea is a class is a bundling of data and functions. That is the core principle of object-oriented programming. That is, you have data, you have functions which are associated with the data. You can see this in the NumPy thing also. We have data which is in terms of this of these 9 numbers, and you have functions associated with the data like come sum, diagonal, dot, and things like that. If I do diagonal, it I have to a dot diagonal will take the diagonal elements. So that's the premise of object-oriented programming. You have data and associated functions. Do you have any questions regarding this, or do you want me to explain a little more?
Yeah, if you could just please explain this, object thing, like
Okay.
how the functions and the data they are bundled together.
Okay. So let's look. I feel I'll. Oh, give me a second. Sorry, my earphones got stuck on my leg. Okay. Now, the important thing. Okay. What I had shown earlier in this part, I just had data. There's just data involved in these things, but having just data is not that useful, because instead of just having data like this, you can just use a dictionary. You can essentially just have student, or we'll call it something else, QWERTY is equal to a dictionary with name is Naveen and age is 25. Like this, if you just want data, you can just make a dictionary. But there are many cases that we need data and certain functions to use with the data. For another example I can think of. Oh, for example, let's consider strings. Here, this is a string, and the data is hello, and I have associated functions. I have functions which make sense for this data. So I can have hello dot capitalize, which takes hello and gives me it capitalizes hello. These are associated functions which are associated with this data. Note that different programming languages call them different things. If I remember correctly, Python calls them methods. My favorite language calls them associated functions. C++ calls them member functions and all those weird names. But essentially, the idea is you have data and functions which are closely linked to that data. So this is not it's not an amazing example. This is an example that just shows that we have data, and the data can do these things. You can also have another important thing you have to note is the data inside the classes can belong to other classes also. I can have a NumPy array inside this. Because this is a class of a student, it kind of makes sense to include marks. And let's just say the marks is random random. I'll just so So in addition to name, age, I also have one more thing for marks. And the one thing you can notice is all of these are different things. Name is a name is a string, age is a number, marks is a NumPy array. You can nest these classes together in these ways. The idea of using classes and associated functions, this is called object-oriented programming, because each of the difference between the difference between a class and an object is the class is the blueprint, the object is blueprints with values inside. Like for example, consider, so there's a shop called, there's Pizza Hut. Pizza Hut also kinds of lets you do these things. So the base pizza is a blueprint. You can add things to the pizza. You can have olives in the pizza. You can have different kinds of cheese in the pizza. And those will be the different data you're putting inside the class. You have a blueprint and you're filling it with data. So an object is an instance. Once again, instance and object, those names differ from languages to languages. Like my favorite language uses instance, if I remember correctly. But the idea is one type of the class, a class with values inside is called an object. Trehan, you have a question?
Just one.
Okay.
You have been referring to that favorite language. So what are you referring to?
My favorite language is called Rust. It has syntax very similar to It has syntax very similar to Python. I can't show anything right now. Okay, it has syntax very similar to Python, but it's a language like C++, so it's a little more involved. Like the reason I like it is its syntax is quite similar to Python. I can show you a control.
Okay.
Yeah, I'll just give a quick folder. Actually, new. So this is code in Rust. If you look, it's kind of similar to Python. You have normal, you have yeah, okay, you have something called a main, but this is just how you define functions. You have something called print line, which prints things in a line, and you even have let a is equal to hello. Like there are small things like you have semicolons at the end of lines and uh, things like that. You have formatted strings and things like that. So it's not that different from cd show cargo run. So it's not that different from Python, but it's a lot more involved. So my friends always joke that if I start talking about Rust, I go for 20 minutes. So I'm stopping already. Okay. Anyways.
Okay.
Yeah. Anyways, the point is, in classes you have classes just have the blueprint. Objects have classes with data inside. The blueprint will also include the functions, but if you think about it, the object will have access to the same functions. So when we talk about the instance, we don't split it in terms of functions and data there. It makes sense to call them together in the first place. But now, in addition to this, let's think of one advantage of having objects like this is another paradigm of object-oriented programming, and that is classes can link to other classes, and this is called inheritance. That is, say I'm making a class. I've made a class for a student, and I want to make a class for a professor now, called a teacher. A teacher will have nearly the same things. A teacher won't have marks, but it'll have nearly the same things. And a teacher will have almost nearly the same functions, right? So it's against the concept of programming to repeat things like this. What we need to do is have something common to both. So I'll make a class called person. Okay, a person has a name, a person has an age. A normal person will just say their name, and it'll just put I am, and it'll just say the name normally as one word, and say age similarly, say name. So I happen to be a person, so we can write me is equal to person of, my name is Naveen and my age is 25. I can say me dot introduce, and it just prints this, which makes sense, right? Now I can inherit a student. Shouldn't just be, I don't want to copy all the code. I want Python to copy the code for me. So what I'll do is class student, and I'll put a colon and write what I want to copy it from. Oh no, it's parenthesis. Yeah. So what I'm doing here is student is a person, whether you like it or not. So similarly, we'll initialize stuff, and when you do if you're using VS Code, it will naturally initialize it with the things in person already. And we also have to super just means the bigger things. It's not necessary for now. In addition to that, we also have marks, so we'll include that. Self.marks is np.array. Sorry, because we are students, we have 0 marks in everything. Why is this useful? Because now I am actually a student. Name is Naveen and age is let's say 25 again. And because a student is a person, we have every function a person has, right? And I can now have the same code for a teacher. This is called inheritance. I'm teacher. A teacher won't have marks though. So that is the idea. And the thing is, each of a student or a teacher can have slightly different things. Like a student is more carefree, so I can have the shout function here. Now, in general, we do not put prints inside. I mean, we can have prints inside, but it's not a good practice to put prints inside functions like this. So instead of that, we'll just return this. Return. Similarly, and you can see the things are almost the same. I just have to put new line. Yeah. Right? So I made a mistake. I should have done this in person. Okay. Return. Return. Plus slash n plus the age. Yes, this is the joy of computing session. Print. So one other advantage of classes is, now if I want to change this, imagine I had made a typo here. Then if I had copy pasted the code, I will have to I have to change the code in every part of the thing. But because of this because of this we have written this code, I only have to change it in very few places. And now here I can have the shout here. Def shout name self. So the idea is we have access to every function, everything as it goes, and this is the idea of inheritance. I hope this part made sense. Do you want me to talk more about classes, objects, and things like that? Because honestly, we can have like excellent diagrams with classes. I mean, to show inheritance. Okay. Mm. So the idea is, right? Oh, I'm blocking. Yeah, it's more visible now. So the idea is both students and teachers have nearly the same things. So in that case, why should I make this different code for both of them? I can just make one code for a person and then use the same code for everything else. So like, and name age. So I hope this section of the thing makes sense to you. So instead of having the same functions and same things, there's so much repeated code here, right? So instead of that, we'll just put can I take a frame? I can't do that. Just take a screenshot, take this, and instead of putting the name and age here, I'll just put it like this. Every student and teacher are okay. So this allows the code to not be repeated, and that's something we really want. So is there any questions? I thought there'd be more questions about objects. It's a very important topic. Okay, so I unfortunately exhausted what I wanted to speak in today's class. So I thought we can go over what was taken in the lectures last week. Yeah, so yeah, this was one of the things I had noticed because this week the lecture topics was essentially about selenium, and I had covered selenium a couple of weeks back, right? So I didn't want to repeat that again. Like I had gotten comments in the QR code I had in the Google form I had linked earlier, saying that people wanted me to cover things that are outside what's taken in the class. So I'd already covered selenium. But if there are any questions regarding selenium, I can answer them again. And yeah, I saw the lectures on calendars, and yeah. Are there any specific questions regarding last week's lectures? So I hope all of you are able to solve the programming assignments. That's good to hear. Okay, so let's look at. I'm not in a. I'm not a huge fan of solving any of these questions today, honestly. I guess we can look at the old assignments, but I don't know if they are marked or if you're. I'm not allowed to show the solutions and things like that. Okay, so do you guys have any questions you want me to solve? Because one thing we can try to solve would be so in the announcements it's written. Okay, so the exact type of questions I'm unfortunately not aware of because we have not been told. We can expect questions quite similar to the questions which are there in the weekly assignments, but unfortunately I do not know additional information about it. I think it'll be a better idea to ask this question in the forum. Yeah, so it's what I expected. There'll be questions like MCQs. Okay, so one thing we can do right now is quickly go over the things we've looked into this class. So, well, we started today's class by going through how to solve a maze. Oh, that reminds me, the to do. In case you see this in YouTube, hey, so I ran the code and it didn't work. So the the color enhanced.png was just a black and white image. So maybe there was something wrong with the code that they had shared with you. So I do not know more about this. I am still if the context is a couple of last week one student asked if converting RGB to black and white is a lossless conversion, and obviously it's not. If when you're converting RGB to black and white, you are losing information. When you're a pixel in black and white image has only 8 bits of data. A pixel in RGB image has 24 bits of data for red, green, and blue. So the student apparently the student got this code from someone saying that the original image can be, we can get the original image using Clahe, but that I ran this code and that's not the case. Anyways, so the first thing we did in today's class was to generalize how we solve the maze. It's very convenient to write a maze using strings. So the first thing I did was write a function which, when given the string, will generate the maze for us. The maze is in the maze is using maze. The maze is stored in maze, and the maze array is the maze in the NumPy format. The advantage of using NumPy format is I can now say I comma j instead of the weird thing I have to do using strings. So once I have made the maze in NumPy as a NumPy array, I can now draw the maze. To draw the maze, I check each element of the maze and compare it to what it's supposed to be. And each element of the maze can be one of these. It's either a wall, a walkway, start, end, or backtrack, or wall off. Wall means you can't walk. It's the wall as you expect. Walkway is the normal thing you walk through. Start is where you start, end is where you end. Backtrack is the way we solve the maze by leaving breadcrumbs behind. So backtrack is what I used to signal that it's a path I've taken, so I have to take eventually. Might have to take wall. So in case I reach a dead end, I will use wall off to wall that dead end off, because if I know it's a dead end, I don't have to go through that entire path again. So this code technically should also work for mazes which have circles. So if I have a path here, okay, if I have a path here, so that's like oh. So now this loop, this path has an entire loop, but this code should the way we had written the code earlier should still run. And if you run this, and it identified the one part from start to end to be this. So like my point was, this code will still work even if it's if there's a loop. We can like make other changes, like if I take the end and put the end inside this place. It will still run. There you go. So here it will do exactly as it's supposed to be doing. It will know that the code is not smart enough to take the shortest path, but depth first search will guarantee a solution. So with that, we can like wind down the class. If there are any questions, feel free to ask. And yeah, I'll be online till 8 o'clock. No, there won't be any marks for watching the videos. They, there shouldn't be. No, but no. I'm not sure, but I'm inclined to say there aren't any marks for watching the videos, because some of they cannot expect you to watch say you already know a little bit of Python and you're only doing this as refreshing some parts of Python. They cannot fail you because you didn't watch some of the lectures. So it doesn't logically make sense for them to assign marks for watching videos. And I don't think it was ever there in any of the. If I remember correctly, the only place where was the weekly assignments and the quiz at the end of every week. So you have to do the quiz at the end of every week, but you did. Oh, it's here. You have to do the quiz at the end of every week, but I don't think you have to. Well, it was written here somewhere. Yeah, they have explicitly written this. So I'm inclined to believe that the videos are not compulsory. Oh, yeah, like I'm using this software for the first time. It's called Excalibur, and it's cool. Okay, so if there are no more questions, have a great week ahead. Oh, so there will be a. I'll probably be taking an extra class on October 22nd for like 1 hour to just cover any questions you guys have and like just cover the entire syllabus quickly just to make sure you don't forget anything. So that's about it. Have a great week ahead and have fun. The class will be ending. I'm stopping the YouTube recording now.